So first and foremost, I would like to thank GEO AquaWatch for giving me the chance to present my work in this event. My name is Avi Putri Pertiwi. I'm working at the German Aerospace Center in Berlin, Germany. The study I've just completed here is titled Coastal Turbid Zone Detection using Sentinel-2 imageries on Google Earth Engine cloud platform. This work is a supporting tool for our main project called Global Seagrass Watch. This project is funded by the German Aerospace Center, and all of our frameworks are performed in the cloud platform Google Earth Engine. In this project, we are developing a cloud-based tool for seagrass and seascape habitat monitoring on a global extent using optical satellite images. In our line of work, suspended sediments on coastal water interfered with light attenuation. Therefore, on areas where the water is turbid, we cannot get a valid information of the benthic classes from the satellite images. In our previous work, these turbid zones were removed from the composite manually prior to mapping. However, it is very time-consuming, and there are also chances that some areas were missed. In the study, I developed a scalable tool to detect the turbid zone where turbidity is persistently high throughout the year. By identifying the turbid zones, it is easier to mask the clear water area for our mapping work. We selected our study sites on the coastal areas where we have observed turbidity in our previous work. The sites are Guinea-Bissau, Tunisia, and Madagascar. We handpicked some turbid zones and clear water points based on visual interpretation for training and validation data. The methodology starts with our water column processor. It works by synthesizing the Sentinel-2 Level 2A image collection, masking out the land surface, and reducing the interferences which are common in aquatic remote sensing, such as sun glint, turbidity, waves, haze, and clouds. As a result, we acquired image synthesis. To separate the clear water and turbid zone classes, we employ three different separating methods, which are Otsu's method for bimetal thresholding, linear spectral unmixing, and random forest machine learning classification with pixel probability output. For the last two methods, we applied probability thresholding between 0 to 100 with an interval of 10 and evaluated them quantitatively and qualitatively. The results are binary maps of clear water and turbid zone classes. On the next slide, you can see the spectral profiles of the Sentinel-2 water-leaving reflectance of the clear water and turbid zone classes. The Sentinel-2 bands shown here are the visual bands, blue, green, red edge, and the near-infrared band. These spectral profiles show that the turbid zone and clear water classes have distinctive pixel values. Higher values are representing the turbid zone and lower values are representing the clear water. Through these spectral profiles, we observed that in Madagascar, the spectral variation between the two classes on the red and red edge bands are much higher than those of the other two regions. And the same thing is also apparent in the variable importance graph. We can see here that the red and red edge bands have higher importance in Madagascar as opposed to Guinea-Bissau and Tunisia, where blue, green, and red bands score much higher. This might be linked to the main composition of the suspended sediments. The suspended sediments along the coastline of Madagascar originates from laterites on the highland. Therefore, the color of the sediments are dominantly red. On the other hand, the suspended sediments along the Guinea-Bissau coastline mostly consist of marine mud, while the suspended sediments in Tunisian lagoons and gulfs are mainly accumulated from nutrients and byproducts of human activities. The dominant color of the suspended sediments along the Guinea-Bissau coastline varies from light brown to brown, whereas along the Tunisian coastline it is of a wide range of hues, spanning from yellow to green and brown hues. Random forest probability classifier with a threshold of 90 yielded the best result, qualitatively and quantitatively. The qualitative assessments were performed visually to confirm that the turbid zones are not over or under predicted. The overall accuracy scores are 88%, 90%, and 96% for Guinea-Bissau, Tunisia, and Madagascar, and the F1 scores are 0.87, 0.9, and 0.96 for Guinea-Bissau, Tunisia, and Madagascar. Presented here are the detected turbid zone marked in red hashed polygons. First one is in Guinea-Bissau. Tunisia and Madagascar. By comparing these three methods, we concluded that random forest probability classifier with a threshold of 90 yields the best result and show the best sensitivity to turbidity, also with a cost-benefit of easier band selection, using variable importance measure as well as easy thresholding. The method is scalable and reproducible for different sites thanks to the VIM that can indicate the relevant bands to represent the dominant colors. Turbid zone detection is highly site-specific. It depends highly on the compositions of the suspended materials and the variability of the benthic substrate. This affects the dominant colors of the suspended materials and also its subpixel compositions. The compositions of the suspended materials depend heavily on the land surface, geomorphology, human activities, and soil nutrients. Additionally, but at a lesser extent, the multi-temporal synthesis, seawater salinity, seabed geomorphology, and the climatic conditions are also affecting the dominant colors of the sediments and the whole aquatic ecosystem. This study can support relevant coastal aquatic remote sensing studies such as benthic habitat and satellite-derived bathymetry mapping, where one can mask out the turbid zone and focus study areas on the clear water regions where the light attenuation is not disturbed. Moreover, this study can also be used to inform local authorities to identify areas for water quality rehabilitation. Thank you for your time and for your attention.